Hello, intermediate algebra students. This is going to be a video that covers 7.2b, which are area problems. There's really maybe a little few different things about this particular section because we're going to be talking about things in a context, finding the area of a rectangle, but otherwise the process of multiplying is exactly the same as what we've learned before. So what I want you to do is have your notes out so you can be ready to go because this video will go through those notes. All right, so first, when we start talking about area problems, we need to talk about what particular shape we're going to be using. And now we could use any shapes, but the particular shape that we will use in this class for this section are rectangles. And if you recall, rectangles have the formula for area, which is pretty simple. It is always going to be base times our height. So area equals base times height. Now, sometimes people use length times width. That is totally fine too. But the B stands for base and the H stands for height. And if you're anything like me, I always was, overthinking the fact which one's the base and which one's the height. It doesn't matter. You're just multiplying the two different side lengths together. Okay. So for an example of what we will be seeing is something where one of the sides is x plus 1 and the other side, I'm not going to be able to write this sideways, is 2x minus 3. Right, so if I asked you to find the area of that rectangle, the area of the whole rectangle, I would need to multiply the base and the height. Well, this turns it into exactly what we were doing on the block day, which is multiplying polynomials. I have two terms in this first one. I have two terms in the second polynomial. So I need to make a 2 by 2 box. I'm going to stick one of my polynomial terms on the top and one on the side. It does not matter which one goes where. And then I'm going to multiply those terms to get the little pieces, little products inside that box. So in this first one, again, you do not have to show this work, but I'm just showing my work so you know how I'm doing this. 2x times x. Well, 2 is the only number. And then when I have an x times x, that's an x to the power of 2. In this next box, I'm going to take 2x times 1, which gives me 2x. In the bottom box, I get negative 3 times x, which is negative 3x. And in the last box, I have negative 3 times 1, which is negative 3. And yes, if you need to use a calculator in order to do some of this multiplication, you can, but you can type x's into your calculator because it will not give you the right answer in these situations. To find the area of this, I am going to add all of these little products together, and that will give me the area of the rectangle. I can combine these like terms. I am going to have minus 1 x's. Now, obviously, this is not telling me the area is 15 or the area is 25, but it gives me an expression that I can use to represent the area. And we will be using this in future units to be able to do this and make it a little more complicated. Continuing in our notes, we have a little bit more complicated problems, as you can see. I'm going to actually start on the right-hand side. The example, oops, maybe, there we go, the right-hand side where we have, oh, okay, can't write up there, I guess. The right-hand side where we have a bunch of rectangles put together. So sorry about that. So when we have a situation like this, we're going to have to find the area of each little individual piece and then combine them all together. So I'm going to need to know the area of this, I'm going to color it purple rectangle. I'm going to need to know the area of this larger green rectangle. And then I'm going to also need to know the area of this smaller blue rectangle. And once I know all those areas, I can just add them all up, and that will give me the area of the total space. So let's start with the purple one. The purple one, if I'm doing the area, is going to be my base times my height. Now in this case, we have a monomial, a singular term times a two-term polynomial. So we could choose to either use distribution or we could use the box. This would be, if I was going to use a box, would be a 1 by 2 box. So it feels a little weird, but the process is the same. I'm going to multiply the things that meet in that box. So in this first one, I would have x squared, and in the second one, I would have just x. So the area of that first rectangle is x squared plus x. Now again, you do not have to use a box for that. You could just use regular distribution. Okay, in this next one, my green box, one of my sides is 2x, and the other side is x plus 5. Again, we have a situation where we could use a box or we could use distribution. Again, for consistency's sake, I am going to use a box, but this time again, it's going to be a 1 by 2 box. 2x times x is 2x squared, and 2x times 5 will give me 10x. So the area of that green rectangle, when I add those together, is 2x squared plus 10x. And then in my last box, my last rectangle here, my one side is x and my other side is x. So I don't even have distribution. Now you could, in theory, I guess, make a 1 by 1 box if you wanted to, but that, again, is totally unnecessary in this situation because you have one term when I multiply those together. Now to get the total area, I am going to add all three, see the answer there, all three of these polynomials together. And then I can combine like terms if they exist, and I can tell they do. So I have an x squared, a 2x squared, and an x squared. So that's really like 1 plus 2 plus 1, which will give me 4x squareds. And then I have 3 x terms as well. I have an x, just 2 x terms. I have an x and a 10x, so that gives me plus 11x. Right, so in that problem, we just really have 3 problems within one. Not so bad, right? In the first problem, this is a little bit more complicated than what we have been doing, because what we're looking for here is not the area of the entire rectangle, but the area of the green shaded region. So I'm going to have to find the area of the entire rectangle, but then I'm going to have to subtract out. I'm going to have to remove that area in the middle. It's kind of like pulling out the whole of a donut, right? I want just the outside ring, but I got to take out the whole so that I don't have that anymore. All right, so the process of doing these, and you'll notice a lot of repetition here, is the area of the big rectangle. And then you'll need to find the area of the small rectangle. And then you will have to subtract them. All right, so we're going to do kind of, again, 3 steps to this problem. We're going to find the area of the big one, the area of the small one, and then we will end up subtracting those 2 answers. Now, the area of the big rectangle here, again, we add a level of complexity because if you notice on the outside of my rectangle, I do not have any dimensions. I don't know the length of that side. I have information to figure it out, but I don't know what it is. All right, so a lot of times these problems will cause your brain to think a little bit more. So if I sort of imagine extending this frame, right, what I've done is I've divided this side into 3 little pieces. And these 3 pieces I know the length of. This top piece I know has a width of 3. And the reason I know that is because this little length right here was measured as 3. You can see that there. Okay, and same for up above. We know that this little length was 3. And I'm just sort of imagining pulling that length over. Now the length from in the middle, from here to here, is also given to me. That is the length of this inside box. It's the same exact size. So I know that this is x. So if I combine all of those little segments together, I have 3 plus x plus 3. And if I combine like terms here, 3 plus 3, I get x plus 6. That is the length of one of my sides of this rectangle, x plus 6. All right, we're going to do the same kind of idea, but along the base of this rectangle, where very similarly, this isn't a very accurate image, it looks like, but we got as close as we could, is I know the, I know the length of the long side of the inside rectangle, this piece right here, that's 9x. So that's the same on the outside rectangle. But the outside rectangle has these little edge pieces that were added, these little frame pieces. And those again are 3 because I know that this side right there is 3 and I know that this side is 3. So in total, that side of the rectangle would be 3 plus 9x plus 3, which would give me 9x plus 6. Be careful when you're combining like terms in those situations, because that's a lot of times people will write 15x there, but we can't add the 9x with the 3's. So now I know I can find the area of that big rectangle by multiplying those two things together. So I'm going to use the box. X plus 6 on one side and 9x plus 6 on the other side. And I'm going to multiply, I lost my ability to change color per usual. I'm going to multiply the terms that meet in those boxes. So I have 9x squared, 54x, 6x, and 36. So the expression for this one would be 9x squared plus 54x plus 6x plus 36. Combining those like terms, I'm going to run out of space here. I'm going to have to write it up here, guys. Sorry. I'm going to get 9x squared plus 60x plus 36. That is the large rectangle. Okay, now going back to our original problem here is I don't want the full area. I don't want this whole rectangle, right? I need to be able to remove the inside area. I need to be able to remove this inside section so that I'm just getting the area of the green spot section. So I need to know the area of that small rectangle. Well, we have those dimensions. This is a lot easier. We know that one side is x and the other side is x. So I can multiply those together pretty quickly to get 9x squared. In order to find the area of the shaded region all by itself, I am going to take the area of my big rectangle, which is 9x squared plus 60x plus 36, and I am going to subtract the area of the small rectangle. Now, typically when we did this in class, when we were subtracting, we put parentheses around these polynomials, but in this situation, those parentheses wouldn't do much because even if I were to distribute this -1, it's still just negative 9x squared. I'm going to combine like terms, which happen to be 9x squared and negative 9x squared, which cancel out and leaves me with 60x plus 36. That is an expression that represents the area of that shaded region. So when you have these things that look kind of like rectangular donuts, you're going to find the area of the big rectangle and then take away the area of the small rectangle. I want to direct you guys to page 8 in your note packet. You have two problems that are very similar to the ones that we just did together in our notes. I would like for you to pause this video, take a few minutes, try to figure out the area of the first and then the area of the second, and then we will check our answers together. All right, so if you look at these two, I have the answers down below. So the answers are in the rectangle. But if you look at the process, in the first problem, we are finding the area of the big rectangle. The area of the big rectangle is our base, x plus 15, times our height, 3x plus 2. So we set up a box, right? So there's a lot of places where you can make tiny errors. So check all of your work. Where in this box, we get 3x to the power of 2, 45x, 2x, and 30. So to get the area of the whole rectangle, I add all of those together and combine like terms. So the 45x and the 2x would give me 47x. Then I have to find the area of the small rectangle, which the dimensions of the small rectangle are 2x and x plus 1. So I multiply those together, and in this case we could use distribution or a box, but we end up getting 2x squared plus 2x. In order to find the area of the shaded region, I need to take the area of the big rectangle minus the area of the small rectangle. Now, a very common mistake that people make here is that they forget that we are subtracting this whole area of the small. So it is important to put parentheses around that and then distribute the negatives. So we would have minus a 2x squared and minus a 2x. So if you didn't do that, you might have gotten one of these terms a little bit off because of forgetting to subtract it. Then I'm going to combine like terms. I have 3x squared and a minus 2x squared to give me x squared. 47x and minus 2x give me 45x. And then this plus 30, don't forget about it, but it doesn't have any like terms. Right, for the second one, this one I feel is a little bit simpler because it involves addition. We're going to find the area of the purple rectangle and the area of the red rectangle, or the area of the smile and the area of the star. The area of the smile, we know the dimensions are 2x plus 5 and x minus 1, so we use a box to multiply those together, which you can check your individual terms, should be 2x squared, 5x, minus 2x, and minus 5. And then the area of the star, we have dimensions of 5x and 2x plus 5. This one we could use distribution or a box, which gives us 10x squared plus 25x. Then to find the area of the whole shaded region, we're going to add those two areas together. When we add, we don't really necessarily need parentheses around our polynomials because distributing them one doesn't change anything. So we just worry about combining like terms, which gives us 12x squared plus 28x minus 5. I hope that helped. I hope you have a great weekend, and we will see you on Monday.